Imagine standing 600 meters above a canyon floor, higher than the Shanghai Tower, with nothing but wind and mist swirling beneath your feet. Now imagine building a road there. Over 2,400 workers spent 5 years and $4.7 billion constructing a single crossing that engineers from Germany, Japan, and the United States called structurally impossible. China built it anyway. Keep watching because you're about to discover how China conquered the devil's throat and changed what humanity believes is buildable. Did you know that some of China's most remote provinces are so cut off from the modern world that a 50-kilometer journey takes 6 hours by car? In the southwestern provinces of Yunnan, Guizhou, and Sichuan, mountain terrain doesn't just slow travel, it kills. Winding cliffside roads claim over 3,000 lives every single year. Villages perched in these highlands are cut off from hospitals, markets, and schools. Children grow up never seeing a doctor. Farmers watch their produce rot because it takes days to reach buyers. Poverty rates in these regions remain 4 times higher than the national average. The geography is brutal. Massive canyons slice through the landscape like wounds in the earth. Rivers rage hundreds of meters below sheer cliff faces. Fog blankets the valleys 280 days per year. For generations, communities on opposite sides of these chasms might as well have lived on different planets. China's Western Development Strategy, launched in the year 2000, aimed to change this, to bridge the inequality between coastal megacities and forgotten mountain villages. But previous road projects crumbled. Landslides swallowed highways. Earthquakes shattered bridges. The devastating 2008 Sichuan earthquake killed 80,000 people and destroyed critical infrastructure overnight, exposing just how fragile connectivity in these regions truly was. Something revolutionary was needed. Before this mega project, engineers tried everything. Tunneling seemed like the obvious answer, but the region's unstable karst geology turned every attempt into a nightmare. Tunnels collapsed repeatedly. In 2011, a single incident killed 12 workers when the mountains simply swallowed the equipment whole. The geology was too unpredictable, the rock too fractured by millennia of seismic activity. Traditional bridges couldn't solve the problem either. The maximum span engineers could achieve was around 800 meters, but the canyon gaps exceeded 1.5 kilometers. You simply couldn't build a conventional bridge long enough. Helicopter supply routes cost $50,000 per trip, completely unsustainable for regular commerce or emergency services. Cable cars worked for tourists, but they couldn't carry freight trucks, ambulances, or the heavy machinery needed to transform a regional economy. Each failure added years of delay and billions in wasted investment. The canyon known as the Devil's Throat seemed determined to remain unconquered. Then came the plan that changed everything. China would span the Beipan River Grand Canyon in Guizhou province with something the world had never seen: a cable-stayed bridge suspended 565 meters above the river below. To put that in perspective, that's equivalent to stacking 4 statues of liberty on top of each other. If you dropped a stone from the deck, it would fall for nearly 11 seconds before hitting water. The main span stretches 1,341 meters, longer than 13 football fields laid end to end. Twin towers rise 269 meters each, taller than most skyscrapers in American cities. The structure would require 60,000 tons of steel, enough to build 8 Eiffel Towers. The concrete poured into the foundations could construct 8 Olympic stadiums. But the most impressive part isn't the size, it's where they built it. The Devil's Throat earns its nickname. Crosswinds rip through the canyon at terrifying speeds. Fog reduces visibility to near zero for most of the year. Temperatures swing from scorching summers to sub-zero winters. Every engineering assumption had to be rethought. The cables were engineered to withstand typhoon winds of 250 kilometers per hour. But wind doesn't just push, it oscillates. It creates harmonic vibrations that can tear a bridge apart, as the infamous Tacoma Narrows collapse proved in 1940. To solve this, engineers installed an active damping system, a network of sensors that detect sway in real time and counteract it with hydraulic stabilizers. The bridge essentially fights back against the wind. This became the first major bridge to use artificial intelligence-controlled drone inspections during construction. Flying robots monitored every weld, every cable tension, every millimeter of alignment in conditions too dangerous for human inspectors. The fusion of traditional engineering with cutting-edge technology created something unprecedented. The challenges didn't end with design. Actually constructing this monster required solutions as innovative as the bridge itself. How do you transport 60-meter steel sections to a construction site accessible only only by treacherous mountain roads. Helicopters. Massive cargo helicopters lifted prefabricated components over mountain peaks and lowered them into position with centimeter precision. Workers poured concrete in sub-zero temperatures, using specially formulated mixtures that wouldn't crack in the cold, and heating systems that kept the material workable. A temporary worker city rose from nothing to house the 10,000-person construction force. This wasn't a camp. It included hospitals, schools for workers' children, recreation facilities, and supply depots. For 5 years, this city existed solely to build a bridge, then largely disappeared when the work was done. The two main towers presented their own puzzle. Rising 269 meters from foundations anchored in unstable canyon walls, each tower had to be perfectly vertical despite constant wind loads during construction. Engineers used real-time GPS positioning systems that could detect movement of less than 1 millimeter and automatically adjust tension cables to compensate. Every element pushed boundaries. The cable stays, those diagonal lines you see supporting the deck, contain over 2,000 individual steel wires each, braided together for strength and redundancy. If any single wire fails, hundreds of others carry the load. The system was tested to 2.5 times the maximum expected stress before installation. But this bridge doesn't stand alone. It's the crown jewel of the Hangrui Expressway, a 2,700-kilometer super corridor linking Hangzhou on China's eastern coast to Ruili on the Myanmar border. That's longer than the distance from New York to Denver. Completing just the section around the bridge required 12 additional connector bridges and 23 tunnels carved through solid mountain rock. The longest tunnel stretches 14 kilometers, nearly 9 miles of underground roadway through terrain that had defeated every previous attempt. A new power grid had to be constructed specifically to run the construction equipment in this remote zone. Traditional infrastructure simply didn't exist. Rail links are now planned to run parallel, with future high-speed trains crossing the same canyon that isolated communities for centuries. The total infrastructure investment for the corridor reached $28 billion, making it one of the most expensive road projects in human history. To put that in perspective, that's roughly what the entire country of Kenya spends on infrastructure in a decade. The promise of this bridge goes far beyond saving travel time, though that alone is remarkable. A journey that once took 6 hours now takes 20 minutes. 6 hours of white-knuckle driving on deadly cliff roads, reduced to a smooth 20-minute cruise 600 meters above the clouds. Economic projections suggest the corridor opens a $12 billion annual trade route to Southeast Asia. Shipping costs drop by 40%. Fresh produce that once rotted during multi-day transport now reaches markets the same day it's harvested. Farmers who were trapped in subsistence poverty can finally access buyers willing to pay fair prices. The construction phase alone created 200,000 jobs. A permanent maintenance workforce of 5,000 keeps the bridge and expressway operating. Tourism has exploded. Extreme tourism packages sell out months in advance, offering bungee jumping from the deck and glass walkways where visitors can stare straight down into the abyss. But the most profound changes are quieter. Children in remote villages can now attend regional schools, instead of walking hours to inadequate local classrooms. Emergency medical transport that once required expensive helicopter evacuation now happens by ambulance on smooth highways. The government projects 3 million people will be lifted from poverty within a decade, connected at last to the opportunities that geography had denied them for generations. A project this ambitious doesn't come without hurdles. Cost. Overruns push the final budget 35% above initial projections. Some economists questioned whether toll revenues could ever recoup the investment, pointing to other mega bridges in China that saw lower than expected traffic in their early years. China's response has been patience and doubling down. The bridge wasn't built for 2024 traffic projections. It was built for 2050, when the connected regions will have developed economies that generate far more transport demand. The chief engineer famously stated that they didn't build for today. They built for the future their children would inherit. Environmental concerns required innovative mitigation. The canyon ecosystem includes endangered golden monkeys and sensitive river habitats. Wildlife corridors were constructed beneath the expressway, allowing animal migration patterns to continue. Advanced water treatment systems prevent construction runoff from contaminating the river below. Reforestation programs are replanting areas disturbed by access roads. The 14 villages relocated to make way for the project received compensation and new housing, though the transition wasn't without difficulty. Managing the human side of mega projects remains one of China's ongoing challenges, balancing national development goals with local community needs. Wind damage to cables during the first year required $180 million in repairs, leading to upgraded protection systems that have since performed flawlessly. Every setback became a lesson incorporated into the 6 additional impossible bridges, now under construction in the same region. International reaction has been a mixture of awe and strategic calculation. The American Society of Civil Engineers awarded it a Global Engineering Achievement recognition, acknowledging the technical brilliance regardless of political considerations. European Union transportation planners are studying the model for potential alpine crossing applications, where conventional engineering hits similar limits. Western engineers describe it as technically magnificent. The bridge has redefined what's considered buildable, putting pressure on infrastructure projects worldwide to think bigger. If China can span a 600-meter canyon in earthquake country, what excuses remain for delayed projects in more favorable conditions? Pakistan, Laos, and Myanmar view the corridor as an economic lifeline, eager for connectivity to Chinese markets and the prosperity that trade brings. The Belt and Road Initiative gains another showcase project, demonstrating China's ability to execute at scales other nations struggle to imagine. Critics remain, questioning long-term maintenance costs and structural durability in such an extreme environment. But the bridge stands, carrying thousands of vehicles daily across what was once an impassable void. What's remarkable is that this bridge represents just the beginning. 6 more crossings deemed impossible by traditional engineering standards are now under construction across southwestern China. Each one applies lessons learned from the Beipan River crossing. Each one pushes boundaries further. The technology developed here, the active damping systems, the AI drone inspections, the extreme weather concrete formulations, all of it transfers to future projects. What seemed like science fiction a decade ago is becoming standard practice. Imagine this model applied globally. Mountain ranges that divide nations could be crossed. Remote communities worldwide that suffer the same isolation as those Chinese villages could be connected. The engineering principles proven above the devil's throat could transform infrastructure possibilities from the Andes to the Himalayas to the Alps. So what do you think? Would you drive across a bridge suspended 600 meters above the earth, higher than any skyscraper in most countries, with nothing but cables and steel between you and the canyon floor? Could this technology connect isolated communities in other parts of the world? Leave a comment below and share your thoughts. And don't forget to subscribe right here so you don't miss more incredible stories about how humans are pushing the boundaries of what's possible, building the future one impossible project at a time.